Hello everyone. So we have already started the sequential circuits. Part 1 introduction we have already seen. Now in the sequential circuits part 2 lecture, first we will see what is flip-flop, what is latch, and then we will study the basic SR latch. So what is a flip-flop? A flip-flop can have one or more inputs. You can see here the basic block diagram of a flip-flop is shown over here. So a flip-flop can have one or more inputs. The input signals which command the flip-flop to change state are called excitations. It can be in the form of the clock pulse. These inputs are used to cause the flip-flop to switch back and forth between its possible output states. A flip-flop input has to be pulsed momentarily to cause a change in the flip-flop output, and the output will remain in the new state even after the input pulse has been removed. This is the flip-flop's memory characteristic. So in this figure, a general type of symbol is used for a flip-flop. So a flip-flop also has two outputs. One is Q and another one is Q bar. Okay. Actually any letter you can use, but Q is the most oftenly used symbol to represent the output. So the Q output is a normal output of the flip-flop, and this Q bar is the inverted output. The output as well as its complement are available, so we can have both the output and the complement of the output. Okay. So the state of the flip-flop always refers to the state of the normal output Q. Okay. The inverted output Q bar is in the opposite state. A flip-flop is said to be in the high state or logic 1 state or set state, ACT state, when these output, normal output Q is 1, and it is said to be in the low state or logic 0 state or reset state or clear state when this Q is 0. Okay. Now what is latch? The term latch is used for certain flip-flops. It refers to non-clocked flip-flops. That means latch with clock signal, we can call it as flip-flops. Because these flip-flops latch on to a 1 or 0 immediately upon receiving the input pulse called set or reset. These latches are not dependent on the clock signal for their operation. That is, a latch is a sequential device that checks all its input continuously and changes its output accordingly at any time independent of a clock signal. So the latch doesn't require a clock signal to operate. Gated latches, that means clocked flip-flops, are latches which respond to the inputs and latch on to a 1 or 0 only when they are enabled. That is, only when the input enable or getting signal is high. In the absence of the enable or the getting signal, the latch doesn't respond to the change in its inputs. On the other hand, a flip-flop is a sequential device that normally samples its inputs and changes its outputs only at times determined by clock pulses. So a latch may be an active high input latch or an active low input latch. Active high input latch means what? That the set and the reset inputs, and the reset inputs are normally resting in the low state, and one of them will be pulsed high whenever we want to change the latch output. Active low means what? The set and the reset inputs are normally resting in the high state, and one of them will be pulsed low whenever we want to change the latch outputs. Now we will move on to the basic SR latch, which is first we will discuss the node based SR latch, which is also known as the active high SR latch. Okay. So the simplest type of flip-flop that we have already discussed is called the SR latch. So as you can see over here, it has two inputs labeled as Q and Q bar. It has two outputs labeled as Q and Q bar, and two inputs it has labeled as S and R, right? The state of the latch corresponds to the level of Q. Okay. Q can either be high or low, and Q bar. Okay. This Q bar is a complement of this Q, and it can be constructed using either two cross-coupled NAND gates. As you can see, this is the logic symbol. So these also can be constructed using two cross-coupled NAND gates or two cross-coupled NOR gates. Here we have shown two cross-coupled NOR gates. That is why we are calling it the NOR-based active high SR latch. So using two NOR gates, an active high SR latch can be constructed, and if we use the NAND gate, then also we can form the SR latch, and that in that case it will be active low SR latch. Okay. So the name of the latch SR, why we are calling it set reset, is derived from the names of its inputs. Okay. So the first figure, this figure, it shows the logic symbol of an SR latch. When this set input is high, what will happen? When the set input is high, Q, the output Q becomes 1 and Q bar will be 0. When the reset input is made high, Q becomes 0 and Q bar will be equals to 1. If both the inputs S and R are made low, then what will happen? There is no change in the state. It means what? It means that the latch remains in the same state in which it exactly was prior to the application of the inputs. So if both the inputs are made high, the output will be unpredictable. That is, both Q and Q bar may be high or both may be low, or any one of them may be high and the other may be low. So this condition is described as not allowed or unpredictable or invalid or intermediate state. Okay. So this SR latch is also called as RS latch. Okay. Or SC latch, set clear latch. Okay. Resetting is also called clearing because we clear out the 1 in the output by resetting to 0. Okay. So here we can see in the figure B, the logic diagram. This figure B shows the logic diagram of the active high SR latch, which is composed of two cross-coupled NOR gates. Okay. So if you notice, the output of each gate is connected to one of the inputs of the other gate over here, right? The latch works as per the truth table. This truth table, which is shown over here, here Qn represents the state of the latch before applying the inputs, that is the present state of the latch, and Qn plus 1 represents the state of the latch after the application of the input, that means the next state. Alright. So if you observe the truth table, what is happening? When set 0, reset 0. When set and reset both are 0, this is the normal resetting state of the NOR latch. And it has no effect on the output state. When both S and R inputs are 0, that means it is the resetting state. It like if your present state Qn is 0, then Q and Q will remain, that Qn, that is the present state. Present state, it will remain in the present state only. That means it don't have, when both S and R are 0, it has no effect on the output state. This Qn and Qn plus 1, Qn plus 1 is the next state. Okay, so Qn and Qn plus 1 will remain in whatever state they were prior to the occurrence of this input condition. So before, when S and R are 0, this Qn will hold its previous state. If it was 0, it will hold to its previous state, and the next state Qn plus 1 also be 0. There won't be any change. If Qn is 1, then Qn plus 1 also be 1. Okay, so there won't be any change. Okay, now what will happen if set 0 reset 1? What will happen when set 0 reset 1? What will happen in that state? This will result Q, when set 0 and reset, when set is 0, reset 1. So this will always reset Q equals to 0. Always remember, whenever, can you observe one thing? This is that 0 0 0 1 1 0 1 1 combination. So apart from the 0 0 and 1 1 state, whenever we have the 0 1 and 1 0 states coming, whenever it is 0 1, because we are discussing an active high SR latch. Okay, whenever it is 0 1, that means S0 and R1. Okay, so it will, the present state will follow the S, the state of the S. So whatever the state of the S is, that will be my present state. You can see, when set 0 R1, present state becomes, Qn becomes 0. It is following, exactly following the S. Okay, so if it is Qn is 0, then Qn plus 1 will also be 0. Okay, then if set 0 and reset 1, in this case, if your present state is 1, then Qn plus 1 will be also equals to 0. Okay, so let me rephrase what I have said. Whenever you are getting the 0 1 and 1 0 combination, so what will happen? This next state Qn plus 1, it will follow the state of the S. Okay, you can see, whenever set 0 and R1, when Qn is 0, Qn plus 1 also 0. It is following the S. When S0 R1, when Qn plus 1 is 0, still the present state is 1, but next state, since it is following S, so it will be 0. Okay, now, so when set is 0, reset is 1, so it will always reset the next state. Qn plus 1 is 0, where it will remain even after reset returns to 0. Okay, now when set is, next third state, set is 1 and reset is 0. Okay, so this will make the next state Qn plus 1 1, where it will remain even after set returns to 0. You can see here also, set is 1, reset is 0, present state is 0, Qn plus 1 will follow set on, set, the state of set only. So Qn plus 1 will be 1. So again, if Qn present state is 1, so Qn plus 1 will be 1, because set is 1. So regardless of the state of the Qn, when the combinations are 0 1 and 1 0, the next state output will follow the S, state of the S or state. Okay, now when both S equals to 1, R equals to 1, this condition it tries to set and reset the latch at the same time, and it will produce the, you can see, even after both the S and R are 1, it will produce both this Q and Q bar 0. Okay, so if the inputs are returned to the 0 simultaneously, the resulting output state is erratic and unpredictable, right? So the input condition should not be used. This is forbidden. This is don't care sign. This is the forbidden state when both S and R are 1. Okay. Now, so this is the present state, next state table. This is the truth table of this SR latch. This is the NOR based or active high SR latch. Alright. Now, next we will discuss the NAND based SR latch. In the NAND based SR latch, this is called the active low SR latch. Previously NOR based SR latch, it is called the active high SR latch. So in the NAND based SR latch, this figure and this figure, it shows the logic diagrams and the truth table of the active low SR latch. Okay, since the NAND gate is equivalent to the active low OR gate, right? Here we are using the NAND gate. So an active low SR latch using OR gates may also be represented. Okay, that you can see over here. So the operation of this latch is reverse of the operation of the NOR gate latch that we have discussed in the last slide. That is why it is called the active low SR latch. If the zeros are replaced by the ones and if the ones are replaced by the zeros in this figure, if the zeros are replaced by the ones and if the ones are replaced by the zeros in the figure, we will get the same truth table as that of the NOR latch that we have just seen. Okay, the set and the reset inputs here are normally resting in the high state, and one of them will be pulled to low whenever we want to change the latch output. Okay, so this is the active low SR NAND latch. Now, this S bar R bar latch, active high NAND latch, is also possible, and active low. So this is the active low NAND latch. So this can be converted into the active high NAND latch. This entire thing is active low NAND latch. So this can be converted into the active high NAND latch by inserting the inverters. You have to insert the inverters over here. Okay, at the S and the R inputs. So we can convert the active low NAND latch to the active high NAND latch. Okay, alright. Now moving on to the gated SR latch. So in the latches that we have described earlier, the output can change state at any time the input conditions are changed, right? So they are called asynchronous latch. But this is the gated SR latch. It requires an enable. You can see it requires an enable input. Its S and R inputs will control the state of the flip-flop only when this enable is high. When the enable is low, these inputs become ineffective and no change state can take place. The enable input, it may be a clock signal. Okay, so a gated SR latch is also called a clocked SR latch or synchronous SR latch. this type of flip-flop responds to the change in the inputs only as long as the clock is high. This type of flip-flops are also called the level triggered flip-flops. We have already discussed level triggering and edge triggering. The sequential circuits that are controlled by the synchronous the sequential circuits that are controlled by the clock are called the synchronous sequential circuits. Okay, so in this is the logic diagram. In the logic diagram, the logic symbol and the truth table for the gated SR latch is shown here. So in this circuit, the invalid state this invalid state occurs when both the S and R are simultaneously high. Okay, so if so here what is happening, you can see when the enable signal is high, then only this circuit will be working. Okay, so when both S and R are 0, whatever the present state, next state will be the same, so no change will be there. When S0 R1 S0 R1, so next state will follow simply the S regardless of the present state. When S1 R0 S1 R0 Qn plus 1, or next state will follow the state of the S regardless of the present input. And when both are 1, we will have this forbidden or invalid state. And when S and R, like when you can't predict the input, okay, so in that case, whatever, when the enable signal is 0, in that case, because the circuit won't work at all, whatever the present state is there, same will be the next state, so no change will be there. Okay,